Alright, we are on lesson 1. Our objective for today says I will be able to order and classify real numbers. I will be able to order and classify real numbers. Before we start, there's a little bit of information in the book that you need to know about. You don't have to write any of this down, but you need to know about it in order for us to understand this lesson. First thing is just a set. A set is a collection of objects. Here are 3 different types of sets written right here. One thing you need to know about a set is that a set is always written within these brackets right here. These brackets show that this is a set. Okay, so a finite set is just a set of numbers that is just the numbers within those brackets. So 12, 24, 36. Those are the only numbers in that set. An infinite set keeps on going. That's what these 3 dots or these ellipses mean. It means that set keeps on going on forever. A null set is just, or a null set or an empty set has nothing in it. So no numbers or no variables within that set. So a set is just a collection of objects, usually going to be numbers. So let's talk about different types of numbers. The first type of numbers that we'll look at are, be sure you are filling this in your notes, natural numbers. Your natural numbers are just the numbers that you use to count things. So 1, 2, 3, 4, 5. Whole numbers are your natural numbers and then zeros. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are whole numbers. Your integers are your whole numbers, so 0, 1, 2, 3, 4, 5, 6, 7, and so on. And then the opposites of all of those. So not only positive numbers, but negative numbers. So -1, -2, -3, -4, -5. Those are your integers. So whole numbers and their opposites. Now rational numbers, what those are numbers that can be written in fraction form. They cannot have a 0 in the denominator. Now what you need to know is that when written as decimals, rational numbers either terminate or repeat. Rational numbers either terminate or repeat. So an example of a rational number would be something like 4/5. Okay? 4/5, when written as a decimal, is 8/10, or 0 and 8/10. Okay? That's a rational number because it terminates. Another example of a rational number would be something like 0 and 6/10 repeating. That goes on forever, 6, 6, 6, 6, 6, but it repeats. That 6 is what repeats, so that is a rational number. So a rational number either terminates or repeats. Okay? Sort of the opposite of that is an irrational number. An irrational number cannot be written in a fraction form. When written as decimals, what irrational numbers do is they neither terminate nor repeat. So neither terminate nor repeat. So rational numbers either terminate or repeat. They do one of those 2 things. Rational numbers do. Irrational numbers do not do either of those things. So let's look at some example. Example 1 says to identify the subsets of real numbers to which this belongs. Now this word subsets, notice that it is plural. That means we are identifying all of the subsets. So an easy way to do this is to sort of look at this chart right here. This chart is in your book on page 3. Okay? Because you can always start with the bottom. Start with natural numbers. What you'll notice is that if a number is natural, so something like 3 is a natural number, if it's natural, it's also a whole number, it's also an integer, it's also a rational number, and it's also a real number. Okay? So, for example, 5. Identify the subsets to which it belongs. Well, is it a natural number? Yes. So if it's natural, you know that it's a natural number, and then again, follow this chart up. It is a whole number, it is an integer, it is a rational number, and it is a real number. And then I close my bracket. So if a number is natural, it's also a whole number, it's also an integer, it's also a rational number, it's also a real number. Okay? Now, we look at this second example, 3 radical 2. Well, first, before we can do that, we have to say square root of 2. Is the square root of 2 even? No. Can you take the square root of 2? No. So what that is going to end up being is a decimal that goes on forever without terminating or repeating. So what kind of number is that? Well, that's an irrational number. So it must be irrational and real. So that would be irrational numbers and real numbers. All of these numbers that we are dealing with today are real numbers. We won't deal with anything except real numbers in algebra. When you get to algebra 2, you'll look at imaginary numbers, but for our class, we are just working with real numbers. So this is irrational because it goes on forever without terminating or repeating. Now, example 2 says to identify the set. Notice that it just says 1, not more than 1. Identify the set of numbers that best describes each situation and then explain. So the first one says the value of bills in a person's wallet. So what I've got to think about is I've got to think about how many bills can I have in my wallet. Well, can I have no bills? Yeah, I can have 0 bills, or I could have 1 bill, 2 bills, 3 bills, 4 bills. Okay, those bills would add up to equal an amount, but we're not talking about change, so we're not going to be talking about just rational numbers. We're talking about either 0 or any combination of natural numbers, so that would be whole numbers. Because it includes 0, and you can have 1 bill, 2 bills, you can't have a half a bill. We're not talking about a bill torn in half. So whole numbers, because a person might have no bills or any number of bills, okay? So you could have 0 bills, you could have 1 bill, 2 bills, 3 bills, 4 bills. You can't have a half a bill, you can't have 3/4 of a bill, so you might have no bills or any number of bills. All right? The second one says the circumference of a circular table when the diameter is a rational number. So in order to figure that out, you've got to figure out what the formula for the circumference of a circle is, because it says it's a circular table. Well, the formula for the circumference is c equals pi times the diameter, and what we know about pi is that that is an irrational number. So whatever the diameter is, if you multiply it by pi, you're still going to get an irrational number. So the subset to which this best belongs is irrational numbers. Irrational numbers. Because circumference is equal to the diameter times pi, and then we also know, so circumference is equal to the diameter times pi, and then pi is irrational. So because pi is an irrational number, we know that whatever the diameter is, whatever this d is, when you multiply it times times pi, you're going to come out with an irrational number. So irrational numbers, because circumference is equal to the diameter times pi, and pi, let me write that where you can read it, pi is irrational. Okay? Next thing we're going to look at is the intersection of events and the union of events. So this is on page 4 in your book. The intersection of sets. Remember, a set is just a collection of objects. The intersection of set is the set of elements that are in A and B. Now, A and B are just variables that they've chosen here to represent these two different sets, but it could be C, it could be D, but here we're just dealing with these two. The union of events is the set of elements that are in A or B. Okay, so union is going to be written with a U, like this, and it's either A or B. The intersection is going to be written with an N, kind of like that, and it's going to be A and B. Okay, so first thing we look at example 3. So I want to find the intersection, which is what this says, and the union. So let's look at A intersect B is equal to the numbers that are in both of these. So I open a bracket to show that this is a set. What numbers are in both of these? I see a 6 here and a 6 here. I see a 12 here and a 12 there. So from greatest to least, I write those two numbers because they are in both A and B. Now look at A, U, not U like that, A, U, B. That's the numbers that are in either one of these. So basically, if it shows up here or it shows up here, it's going to be in this union. So I see 2. I start from the least 2, 3, 4. I see a 6 in both of them, but I only want to write that 6 once. So 2, 3, 4, 6, 8, 9, 10, and 12. Okay? That's my union because it's everything that's in either one of these. Same thing here. I want to go A intersect B. Anything that is in both of these. I'm looking for a number that is in both A and B. I do not see a number that is in A and B. They have nothing in common, so I write an empty set, just like that. There's nothing that is in both of them. Now, what about things that are in either one of them? Well, again, I just go from the greatest to least and list all of these numbers. So I go 11, 12, 13, 14, 15, 16, 17, 18. If it's in either one of those, then it's in the union. If it's in both, it's in the intersection. Okay? Last thing that this wants us to do is to talk about closure. Now your book tells us that a set of numbers has closure or is closed under a given operation if the outcome is also a set of the member of the set. Now what does that mean? Basically, let's look at this example. Is the set, so determine whether this is true or false, give a counterexample for false statements. So the set of whole numbers is closed under addition. It's true that it's closed under addition if every time you add a whole number, you get a whole number. That is true, and let me tell you why. So true, the sum of any two whole numbers will always be a whole number. The sum of any two whole numbers will always be a whole number. So any whole number that you choose, 0, 1, 2, 3, 4, 5, 6, 7, 8. You choose any number. So let's say 4. You choose any other whole number, 0. You add those together, 4 plus 0 is 4. You get a whole number. For it to be closed, that means that every single time you perform that operation with that set of numbers, so every time you perform addition with the set of whole numbers, will you get a whole number? Yes. Any whole number that you add to another whole number, you get a whole number. Okay? Now, let's look at this one. The set of whole numbers is closed under subtraction. Is that true or is that false? Well, I'll tell you that that is false. And here's why. It says to give a counterexample for false statements. Well, let's take a whole number 0 and let's subtract another whole number 8. What do I get? I don't get a whole number, I get negative 8. Okay? Negative 8 is an integer. Okay, so anytime you subtract a whole number, you don't always get a whole number. Let's try one more. Let's take a whole number 4. Let's subtract another whole number, 12. 4 minus 12, again, gives me negative 8. Because this is negative, I know that it is not closed. Let's try one more. 3 minus 4 gives me negative 1. These are negative numbers, which are integers, which are not whole numbers. So it is not closed under subtraction. That is it for lesson 1.